Okay, so going to go through some examples now. So here's the first one we're going to look at, which is solve dy dx equals log of x, given that x is greater than 0, if y equals 2 when x equals 1. So solve dy dx equals log of x for x is greater than 0 if y equals 2 when x equals 1. I'm just going to write the question down again just so I can sort of go from there. It's up to you whether you do that. Okay, what was the first thing we did? On that very basic example we recapped this morning, what was the very first thing that we did? If you look back in your notes from last time, it's the first sort of box thing that I put down. Yeah, I call it separate the variables. Okay, separating the variables, which means get all the x's on one side or the y's on another side. So if I leave the dy where it is, I'll leave the y's on the left because there my dy is on the top of the fraction. Being on the top of the fraction is better than being on the bottom of the fraction. So I'll leave my log x over here and I'll just move my dx, which is a dividing dx there, up here as a timesing dx. So that was step 1, separate the variables. What was then step 2?
When do we do this?
Did it a week ago. Yeah, integrate both sides. Okay. Step 2 is integrate both sides. So basically just stick an integral sign down in front of the left hand side and the right hand side. And here, if there's nothing between the integral and the dy, it might be easier if you put a 1 in there. It does make it a little bit easier to work out what's going on, particularly at the beginning. So, can somebody integrate the left hand side for me? Why? Yeah. Okay. Has anybody remembered the result I said was useful to remember, which means we can integrate this one? Yes. Okay. Yeah. X log x minus x we said was a very useful result to remember for the integral of log of x. And then usually on the right, and only on the right, we put the plus c. You could put a plus c1 over here and a plus c2 over here, and then you could move that c1 over this side, combine it with the other one and just get a different c. So we just usually do it on the right.
Why can you do like mess around with dy over dx? Why can't you just integrate it?
It's usually, well, you can't integrate something like this usually unless you've got a d something there, which is the same as what's in here. Because if you didn't have a d, if you just put an integral sign there, you don't know whether you're integrating with respect to x or whether you're integrating with respect to y. Every time you've ever come across anything you're integrating, there's always been an integral sign on the left and a d something on the right. So we're writing it still in that format.
So is it just to show mathematically what you're doing?
Yeah, and to show that we're integrating it with respect to x, not with respect to y. If we integrated that with respect to y, we would get something different. So we have that line there. That line is our general solution. It's y equals something. That's our general solution. But in this question we were given some other information at the beginning. We were told that y equals 2 when x equals 1. So I'm going to put it down like that as a coordinate, basically my x number and my y number. When y was 2, x was 1. So if I use that and substitute in, I'll get 2 equals 1 log 1 minus 1 plus c. Now, what's log 1? 0. So that bit disappears. So I get 2 equals minus 1 plus c. So c must equal 3. So now I just rewrite my general solution, but I just change the plus c to be a plus 3, and that line there is my specific solution. And that is the end of that example. So, we all happy with that one? Okay, let's move on then to another one. Okay. So, solve x dy dx equals minus tan y if y equals pi by 3 when x equals 2, and we have to solve it, we have to give our answer in the form x sine y equals k, and we have to find out what that k is. So I'm just going to write the question down again here, just so I can show very clearly what's going on here. Okay, what's the first thing we should do? What was the first thing we did in the other one we've just done this morning? Well, yeah, I'm calling that separating the variables. Okay, so the first step to do is separate the variables, which means get all the x's on one side, all the y's on another side. Which is the best side to have our x's on? Which is the best side to have our y's on? Sorry?
X on the right.
Yx is on the right, and you are correct.
So it's the general formula we've been doing.
Okay, it's one way of thinking of it. It's not probably the best way of looking at it. But if the dy is on the top of the fraction, then have the y's on that side. You don't want to end up with a d anything on the bottom of the fraction. So I'll keep my dy where it is. I will move the x to the other side, where it will be on the bottom of the fraction. I'll move my dx up here. And I'll move my minus tan y down there. So now I've got all my x's on one side, all my y's on the other, and all my d bits are on the top. None of them are on the bottom. That's what you're really trying to do. That makes life easier. And the next thing was to integrate both sides. So I can just put an integral sign in. I'm going to write this slightly differently here. Which of those sides is nice and straightforward, hopefully, to integrate? This one over here, yeah. This one over here. Anybody think of anything we could do that may help in integrating minus 1 over tan y? Sorry?
Right as x to minus 1 instead of... Oh no, yeah, sorry, that was doing down goes to log it.
Cot. That is the same as cot.
Oh, I thought we were talking about right, sorry.
No, yeah, we're talking this side over here. It is the same as cot.
And then you can just look.
What's cot the same as? Cos over sine. Yeah. Tan is sine over cos. So 1 over cot, 1 over tan, which is the same as cot, is cos over sine.
Would that be in the formula?
No. You need to know that tan is sine over cos.
No, with the integration of 1 over tan.
No, that's not either. It might, I can't remember, without looking at it, I'd have to check and see. But if we've got this, what is now missing on the left?
Negative.
So I'll put that there. Okay, that negative sign. Now, can anybody spot why what I have done has been useful?
Do you have a sign in there? They want sign in the
Yeah, they do want sign and final answer, so that could be a good reason.
Oh, because the top is differential.
Yes. Well, what I've got here, I've now rewritten this as an integral where the bottom function has its derivative on the top. That's what I've got there. And when I integrate that, what do I end up with?
Log of sine.
Well, log of the function on the bottom, okay? So that's the red box rule I'm using here. If you can get an integral, which is a fraction, where the top is a derivative of the bottom, that ends up being log of the function on the bottom. And here, cos is the derivative of sine. So actually, that's pretty useful there. I can use that fact. So using that, can somebody tell me then exactly what I will write down for the left-hand side being integrated? Log of sine x.
Some y.
So yes, it is a y there actually. Yes, it is a y. And Corey, you also said yes, that minus has got to come down as well. Yeah, so minus log sine y. Okay, using that result there. And on the right, the integral of 1 over x. log of x. And because I'm integrating on the right hand side, I'll put my plus c. Now the question said I had to have this in a different form, and it also gave me a pair of values which I could substitute in, because at the moment this is heading towards a general solution, but what I can do is remove that c by using the values that were given to me. I was told that when x was 2, y was pi by 3. So I can substitute those two values in at this point, and I can find out what my c is. So on the left I get minus log of sine y equals log of x plus c. Right, so I need to do what sine of pi by 3? We need to be in radians. If we're doing anything to do with calculus, integration and differentiation, we need to be in radians.
Third with a square root sine over 2. 3 with a
root 3 over 2, yes. Sine of pi by 3 is root 3 over 2. Okay. Log of 2, well, that's just log of 2, isn't it? So we've got that. Really, I needn't have said to see what I just said about the radian thing, because you'd converted it into degrees, haven't you? And we're then going to do that, that's fair enough. Okay. So from here, how do I go and find out what c is from here? What would be a good thing to do? Get all the logs on one side, yeah. So if I leave the c over there, and I'll leave this log here, this has to come over the other side. It's a plus log 2 over there, it's a minus log 2 over here. Okay. What can I do here then?
You can split the natural log into
this one here.
minus root 3 minus.
Well, I'm going to cover up that minus sign for a minute. Just look at that bit. What can I make that bit, Corey? Doing what you're saying.
But natural log of root 3 minus natural log of 2.
Yes. Okay. When you have a fraction, so what we've done there, we've used the fact that log of a over b is log of a minus log of b. That's what we've used there. But all of that has got a minus sign in front of it, and in front of that there's a minus log 2. So what I've got here is minus log 2 minus minus log 2. So it's got a minus log 2 plus log 2, so that will disappear. And all I'm left with there is minus log 3. So c is minus log, sorry, not 3, root 3. I'm going to pause the video at that point because I'm just running out of time for this clip, and I'll carry on again in another clip.